Welcome everyone to the 2023 Paul Bernays Lectures of ETH. So on behalf of the organizing committee, I'm very happy to welcome here Kevin Buzzard from Imperial College. So let me remind you first of the nature of this lecture series. So these were created 12 years ago now by Professor Giovanni Sommaruga from Deges, and it's a series of lectures held every year, rotating between the topics of computer science, mathematics, and physics, with a focus on people's work and achievements having to do with philosophy of science and foundational aspects of their respective sciences. So the Paul Bernays lectures are named after Paul Bernays, who was a famous logician, mathematician, philosopher of science from the 20th century. So born in 1888, died in 1977, born in London, died in Zurich. And he was a professor in various capacities at ETH from 1933 to 1959. So the achievements of Paul Bernays began with a PhD in number theory. This is a not so well-known fact for people who know him mostly for his achievements in logic and philosophy. So this is a common point with Professor Buzzard from Imperial College. So Professor Buzzard had his PhD in 1995 under the direction of Richard Taylor at the University of Cambridge, and it was in number theory, arithmetic geometry, and the Langlands program. From that point on, he had various positions, achieving a professorship at Imperial College in 2004, and was one of the leading lights of the Langlands program and arithmetic geometry more generally until about 2017, when he started a slightly different type of work, which is what he will be talking about, which is the problem of formalizing mathematical proofs using computers in order to make sure that these proofs are rigorously correct. As maybe we'll give examples, they are in very respected journals, published papers proving a theorem and its opposite, both published, both accepted, none of them rejected, in the same very, very highly respected journal. So this is the kind of thing that for mathematicians is potentially problematic. And so Kevin has been in particular one of the leading lights in trying to convince mathematicians to formalize not just simple objects and complicated proofs about simple objects, but also the kind of sophisticated abstract mathematical objects that occur, for instance, in this Langlands program and arithmetic geometry. And among the recognition that this program and these ideas have had, so he gave a plenary lecture at the ICM last year, and he will then talk to us over 3 days about this whole circle of ideas. Please.
Thank you very much. So thank you for coming. I thought it was holidays, but here you are. And thank you very much to Emmanuel and ETH for the invitation. So I'm giving 3 lectures. So let me just tell you what the 3 lectures are about. In the first one, I'm going to talk generally. This is quite a soft lecture. You don't really even need to be a mathematician to follow it. But it's about new tools which are appearing in computer science, which mathematicians might be able to use and are using. In the second talk, I'll focus on one of these tools, interactive theorem provers. A lot of this first talk will not be about interactive theorem provers. It will just be a sort of a general talk about what's happening in computer science and how it might affect mathematicians. And in the second talk, I'll focus on interactive theorem provers. I'll show you how they work. And in the third talk, there will be some mathematics. I'll talk about one mathematical project I was involved in, which is completely unlike any other mathematical project I'd ever been involved in before. So there's the 3 talks. So this is the first talk. It's a very general question about whether AI techniques are actually going to disrupt mathematics. So what tools can the computer offer the modern mathematician? That's the question. There's traditional mathematicians use computers traditionally they use them to do boring, repetitive tasks quickly, and I'm going to say very, very little about that use of computers. So the idea about this talk is that there are other things that have happened in the last decade or even more recently, which are giving us new ways to use computers. And this talk is sort of going to be an overview of those things. So let's go. Let me just do 2 slides on traditional uses, even though most people in the room will be very familiar with these things. So how do we use computers traditionally? The idea is that even before computers were machines, people were still talking about computers, but they were humans doing calculations. And one early example of computers really changing mathematics, giving us insights, is that in the late 1700s, these 2 human computers, Felkel and Vega, they factored every number less than 408,000. They broke all of those numbers down into prime numbers, and as a consequence of their work, they worked out how many prime numbers there were less than 408,000. That was they were the ones that didn't factor. And in fact, even more than that, they had a graph, right? You could make a graph, you could plot number n against number of prime numbers less than n. So that data was available to people like Legendre, who was a mathematician, and he looked at this graph and decided that what it looked like was happening was that the number of primes less than n was approximately n divided by log n. And so this was a question he raised in his book, I guess late 1790s, and this conjecture is now called the prime number theorem because it turned out to be true. That is a very good estimate for the number of primes less than n, but it took 100 years to prove. So it was discovered. Because the computers played a key role in its discovery by doing all the tedious work to collect the data, but then the mathematicians were the brilliant ones, right? The mathematician had the idea, and he saw the pattern and figured everything out. So that's one slide, and second slide is just the same story. The only difference here is that by this stage, the computers had become machines. The computer in this case was the EDSAC-2, which was the size of a large room and had several orders of magnitude less memory than your phone. And during the day it was being used, and it also cost a lot of money. And during the day it was being used to sort of do tectonic plate predictions. The modern tectonic plate theory was developed using this machine during working hours. But then when all the tectonic plate people went home, sort of Swinnerton and Dyer would sneak in the evenings with his punch cards, and he would get the computer to answer questions like this. So here's a random cubic equation with integer coefficients in 3 variables, and the question is, how many solutions are there? Modulo 37. So they got the machine to do hundreds and hundreds and hundreds of these very tedious calculations, and ended up with a nice collection of data. And then they drew some graphs, and the art is now which graph do you now draw? Eventually they came up with something, and it turned out that this something, after a few more years, became what's now known as the Birch and Swinnerton Dyer conjecture, which relates the behavior of the rational solutions to this equation to the number of solutions modulo p, and this conjecture opened new. It's now the conjecture has been generalized out of all proportion. It's now a very simple special case of some far more general conjectures, but it's still completely open. I mean, there's been lots of results, but it's still an open problem. And furthermore, if you solve it, you get $1 million. I think you have to prove it. I think if you disprove it, you don't get paid. But if you prove it, you just write down one cubic equation and note that it doesn't work. But of course, people have written down thousands of cubic equations and it works for all of them. So this So it's the same story, right? The computers did the boring part, did all the calculations, and then the humans looked at the data and found the symmetry and found the pattern and found the profound link. And that's how it worked. So that was my mental model of the way that, the way that computers were used to do research level mathematics. So as I say, the computer is just doing the tedious mechanical calculation, and it's the humans that are being brilliant. So they say, mathematics is 1% inspiration and 99% perspiration. So I guess it was the computers were doing the perspiration here. And so that's the past, and now the question is, what about the future? And the ridiculous thing is that if you believe some people on Twitter, for example, if you believe Christian Szegedy, who's a very sort of serious AI researcher who works at Google, and his most cited paper has got more citations than your most cited paper, because his most cited paper has got 30,000 citations, where he solved some hard problem in computer vision. So he knows what he's talking about, and he's been arguing, since I met him in 2019, he's been arguing that mathematicians are going to be out of a job soon, because computers are just going to take over. They're going to start thinking for themselves, proving theorems that we can't prove, and we're going to be out of a job. So I'm going to spend half an hour sort of making fun of this idea, because I think that's a ridiculous idea. But I don't, it's very easy to just speculate what will and won't happen in 10 years' time or 20 years' time. But what I'm actually going to do is I'm going to do something more reasonable. We're going to look at the evidence. We're going to look at what has been going on and what's currently happening, and then I'll leave it to you, to extrapolate what will happen next. So that's, this is not going to be a talk full of outrageous claims. This is, going to be a talk full of facts. Because, I don't know, I'm a mathematician, so I kind of... So here's a very naive, appealing argument that says that mathematicians are going to be, out of a job within the next decade. Here's how it goes. Let's start with chess, because chess is a game that has well-defined rules. I mean, chess is sort of an open game in that, you don't hold any secret cards that your opponent can't see, and you don't roll a dice, and there's no element of chance involved. Chess is a perfect knowledge two-player game, and in the 1990s, IBM decided to solve it, and they didn't. I mean, chess is still not solved, but what they did do was they made a machine that could play chess much better than all the other chess computers. Chess computers in the 1980s were very weak things, right? Chess computers in the 90s, people would say, I was an active chess player in the 1980s, and my impression was that the general prevailing opinion was that, there's exponential blow up in number of positions, and this would stop any machine from doing anything, because you can't beat the exponential growth. And it's true, in the 1980s, the best chess computers were very weak. But in the 1990s, a big company decides to try and do something. So they put together a huge database of openings, and they put a team together, and they won. They did it. By 1997, they had a machine that beat Garry Kasparov, the current, the then world chess champion. So they had a machine that had become superhuman at chess. So more recently, Go is a game. It's much bigger than chess. It's a sort of oriental board game played on a 19 by 19 board, and just the same thing. It's a zero. There's zero secret information involved, and this was for a long time regarded as this is not an obscure game. This is an incredibly popular game in some parts of the world, and but it's much, much, much bigger than chess. If you want to play, you can imagine the first 20 moves of a chess game. There's going to be some large number of possibilities, but the first 20 moves of a Go game, there's going to be 10 to the 20 more possible. There's at least 10 times as many moves you can make in Go. than in chess at any point. So it really does become incredibly unwieldy very, very quickly, and sort of traditional analysis isn't going to work at all. But this computing company, DeepMind, based in London, now owned by Google, they developed a program which became superhuman at Go. And so just the same thing, beat the world Go champion. And rather more, somehow surprisingly, is that they didn't even need a database of several 100,000 expert Go programs. The system just learns by playing against itself. So you let it play against itself millions of times, and then it invents. They have it. It can also become superhuman at chess in a 24-hour period as well. You just leave it to play against itself at chess, and it just invents many well-known chess openings. So it's really quite extraordinary what these things can do now. And so, of course, now the computer scientists tell us, board games are solved, right? In the sense that if there's any kind of game of this nature, that in theory it would be possible to design a computer program that could beat you, however good you are, even if you're the world champion at that game. So board games are now solved, and of course mathematics is it's not just about proving theorems, right? Mathematics is about having insights and connecting things together and making conjectures. Mathematics is about lots of things, but certainly one key component of mathematics is about proving theorems. And proving theorems is a game, right? Proving theorems is a puzzle game. It's got completely well-defined rules. Those are the rules of mathematics. There's nothing secret going on, no chance or anything like that. And so it's a game. So we've got all these techniques that solve games, so we can just throw them at mathematics and solve mathematics. So that's the naive argument. And it turns out that it doesn't work. I mean, it's great in theory, but it just doesn't work at all. You try it, and you can't even get as good as an undergraduate. So these things are kind of like, chess computers in the 1980s. And just as a chess expert in the 1980s would be skeptical about computers taking over, I think it's not unreasonable that a mathematician can look at that and then remain skeptical. So these things cannot. These tools that have been developed to solve board games, you can't use them to solve mathematics, and there are reasons for this. So just let me give you some kind of idea as to why it's not so easy. So the first sort of serious difference is that, you are allowed to do mathematics with collaborators, right? It's not just a single player game. You can work with other people, but when you're collaborating, you tend to be trying to prove the same theorems. You tend to be on the same side, right? There's only one side in mathematics, whereas in chess you're playing against your opponent. And a move that's good for you is bad for them. So mathematics is a puzzle game. It's a one-player game. In that sense. So that means that you can't learn mathematics by playing against, you can learn chess by playing random moves and then starting to play less random moves as you kind of begin to get the hang of moves that somehow increase your winning probability. Hello. Hi. I'm not really supposed to be taking questions, but go on, just because it's you. Yeah. Okay. There's lots of other reasons as well. Here's another reason. Another thing, you're right, but I think this problem doesn't solve. The thing about chess is that you can look at a position and you can attach, and mathematicians like attaching numerical invariants to data. Right? And so you can look at a chess position and you can say, well, let's have 1 point for the pawns and 5 points for the rook. And you can come up with some number, and if the number you have is highly positive, then maybe you're winning. Whereas if you're proving a theorem, then in my experience at least, most of the time the situation is you're stuck. Right? You kind of got some ideas and you can't make them work and you're stuck. And so the total number of points you have here is 0, right? Like when you've solved it, you get 1, and when you haven't solved it, you get 0. So this is not a good reward function. Whereas, if you have the chance to take your opponent's queen in chess, then it doesn't matter if you can't prove that 30 moves later you're going to win. You can just see that this is somehow a good idea, because the numerical invariant sort of shoots up. So we don't have these obvious numerical invariants. And in fact, I do remember, sometimes you see some proofs and you're kind of thinking halfway through, where is this even going? Like, why have we introduced this crazy auxiliary function? What is going on? It looks like you're taking some crazy route round. So it's sort of difficult to give a good reward function for theorem proving. And then another problem is that, in the lingo, mathematics has got a large search space, but an infinite action space. At any point, you can do infinitely many. You could add 1 to both sides, or you could add 37 to both sides, or you could apply one of many theorems. There's two. Even though there's 300 moves you can make in Go, you're still confined in some sense. Mathematics is sort of very, very liberal in that, as long as you abide by the rules, you can do whatever you like. And these three facts put together somehow derail these standard techniques. So just before I leave this topic of mathematics as a game, let me advertise tomorrow's lecture. So one thing about games is that if you like a certain game, but you can't find someone to play it against, you could download a program onto your computer and you could play that game on your computer. And I've been arguing that mathematics is a game, and so nowadays it's possible to do just the same thing with mathematics. You can download a program onto your computer, and you can make levels. You can make levels in that. This program is a puzzle game, and you can make a level in that puzzle game, and that level corresponds to a mathematical theorem, and then solving that level corresponds to proving the theorem. And that's something that I find very appealing and sort of fun and interesting. And I'm going to say very little about these things today, but tomorrow, that's what this talk is. Tomorrow, that's what the talk is going to be about, how to play with interactive theorem provers, and I'll be talking about how humans play with them and how computers play with them. But right now, humans have got the upper hand with these games. We're much better at playing these games than computers. So more on that tomorrow. Let's talk about some different things today. And the first thing I want to talk about really is large language models, because everybody's heard of ChatGPT. So let me talk about ChatGPT doing mathematics. So what's a large language model? A large language model is something that plays that game. It plays the what's the next number in this sequence game. So what's the next number in this sequence? I guess that's not too difficult a question. But it doesn't have to be numbers, right? You could play it with words. What's the next word in this? I don't know, in this sentence, that would work. Or more generally, if you want words and numbers at the same time, you could play it with tokens, right? There's a nice computer sciencey word. What's the next token in this sequence of tokens? And a large language model is simply a computer program which has been trained to play this game. And you might well have found that over the last year or so that your email client has learned how to play this game. It might you're in the middle of typing an email and you might suddenly notice that the system is suggesting the next word you might want to type. And you can do that. Some mobile phones as well. You can just, my daughter does this. Somehow this is a thing. You start sending someone a text and then you just stop at some point and you just predict the next word and you just let it write. Stuff that inevitably turns out to be nonsense, in fact. But it's that's the game that we're talking about here. What's the next token in this sequence? And the most famous of the large language models is ChatGPT, which is it plays this extraordinarily well. But there's other examples as well. It's not just ChatGPT is written by OpenAI. Microsoft has a version as well that they've attached to their search engine Bing. So you can talk to Bing not just as you don't just ask it to search the internet. You can ask it to answer your question. And Facebook as well is also very interested in these large language. I mean, people really my talk is about using these tools to do mathematics, but these kinds of tools have got huge applications well beyond mathematics. So lots and lots of tech companies are interested in these tools. But as I say, I'm just focused on, can we actually get these tools to do something that we as mathematicians would find useful? So the systems used to be rubbish, and then there was a breakthrough paper a few years ago. The systems used to, they would sort of forget what they were talking about. They were talking about a topic, and they last mentioned it 15 words ago, and now they're still guessing what the next word in the sequence is, but they've sort of lost track of that word, and they're doing something too local. And they just end up writing incoherent sentences that go on for far too long. But then there was this sort of breakthrough about how to sort of track the stuff that had happened several sentences ago. And now these things can write coherent paragraphs of text. And so now the next thing is, so now you have to train it on something. The idea is you give it lots of examples of tokens in a big list, and then you say, this is, here's some examples of the game I want you to play. Now go and play this game. And so one good example of a large list of tokens is the entire internet, or at least I think the English language speaking internet. OpenAI were extremely vague about exactly what went on. Like, we don't really have the details of what they did or how much it cost them to do it. It could have cost them millions, or possibly even hundreds of millions to train this model. But somehow they've trained something, and they say that they trained it on the internet in 2021. And all it is just guessing what the next word is in this sequence. So in particular, it's not doing any kind of reasoning or logic. And this is the big problem. It's guessing what comes next, but it's not thinking. And so you can ask ChatGPT what 7 4s are, and it will reliably tell you that 7 4s are 28, and that's not because it worked out 7 4s. It doesn't have any kind of algorithm for doing multiplication like that. But what it does do is it's seen people write 7 times 4 equals on the internet, and then the next token after that is 28, 9 times out of 10. So the idea is it sees the tokens you've put in, and then it makes some probability distribution, and then it chooses a token at random based on that distribution, and it's going to choose 28. And so if you ask it to multiply 2 10-digit numbers together, then of course, if they're random 10-digit numbers, then it won't have seen them on the internet before, and you might run into problems. So I didn't know if this was going to show up, but that was me using ChatGPT earlier today. I asked it what 7 4s were, and it told me that 7 4s were 28, and then I chose 2 random 10-digit numbers and asked it to multiply them together. And it looks good, right? It's just not right. It confidently tells you what the answer is. And it's close, it's not bad. So I'll tell you, the first 3 digits are right, the last 3 digits are right, and the number of digits is right, and all the digits in the middle are just made up. You see, because the system has seen lots of numbers being multiplied together, and it's noticed that if the first one ends in 6 and the second one ends in 5, then the answer ends in 0. And so it gets the last digit right. And it notices, the first one begins in 7 and the second one begins with 6, and so the answer probably begins with 4. But in the middle, it's not actually doing mathematics. You can see why this would happen if you do what they did. You train it on the internet, and the internet doesn't contain the answer to every question. In particular, it doesn't contain the answer to that question. So that's what happens. Okay, so great. So that's not a very good start, but let's forget about that. What about theorems, right? That's what we're really interested in. So let's try and prove some theorems using a large language model. Let's try and prove there's infinitely many primes. And this is a great example of something that you hope it will do well, because there's lots and lots and lots of proofs on the internet that there's infinitely many primes. So, I didn't really know if people were going to see that. If that's too small for people, don't worry, because the key argument is going to be on the next slide, much bigger. But let me just whiz through what this says. I ask it, can you give me a proof there's infinitely many prime numbers? And the computer says, yes, I can provide a classic proof called Euclid's proof of the infinitude of primes. And then it gives the proof. Assume there's only finitely many, multiply them all together, and add 1. Right? That's the correct step. I mean, let's say I put this on my Introduction to Proof course exam, and I've got 300 of these scripts to mark. Right? Let's imagine I've got to decide if this is worth 10 marks, or I've got to give this some mark out of 10. But I've got hundreds of scripts, so I just want to get. I mean, clearly this is the correct first line. N is either prime or composite, and if it's prime, then we're done because it's a new prime. And if it's composite, then there's a prime factor. This looks fine, right? So clearly this is a 10 out of 10 answer, right? Now let's go on to the next one. So now let's actually read it properly, and let's make it bigger so we can all read it instead of just me. So what did it say about the composite case, right? We've got to prove there's infinitely many primes, so we've got finitely many primes, P1 up to Pn, and then we add 1, and we've got this large number, capital N. And what about when capital N turns out to be composite? Because that can happen, right? And this is what it said. It said if N's composite, then there exists a prime factor P of N. I mean, that's okay. 1 is... that's okay because N is bigger than 1. Since P is a prime factor of N, it must divide P1, P2 up to Pn. That's not actually right. It must divide P1, P plus 1. It must divide P1, P2 up to Pn because it divides the product of these numbers plus 1. However, P cannot divide any of the Pi because Pi and P are co-prime for all I. This is sort of the kind of... One thing about the internet is that the internet isn't 100% correct, right? The internet's it'll have a lot of proofs of the infinitude of primes, and not all of them will be, some of them will be a bit muddled, right? And what we have here is a sort of a slightly muddled proof, where the key ideas are there, but the details aren't sort of quite adding up. So it's not really a 10 out of 10 solution. But on the other hand, it's clearly, it's much better than 5 years ago. 5 years ago, it would not have written a coherent English sentence. So you can see that there's been exponential increase in what's going on. But it's not quite there. Okay, so great. So let's now ask a harder question. Let's prove there's infinitely many primes that end in 7. And now that's hard. Right? But the thing is, this is a good example because this gives you a feeling as to what these systems can do. So the reason this is hard is that you do the same kind of thing. You've got finitely many prime numbers that end in 7. You put them all together in some way. Multiply them all together. I don't know. Multiply by 10 and add 7. Right? That would give us a new large number that ends in 7. That might work. Now the problem is, in the composite case, that large number ends in 7, but it could easily be the product of prime numbers that don't end in 7. So the standard proof doesn't work, and indeed this theorem is hard, right? So here's me. Yeah, can you prove there's infinitely many prime numbers that end in 7? Yes! Yes, I can prove there's infinitely prime numbers that end in 7. And it just does exactly what you think, right? So say there's only finitely many. Take all these prime numbers that end in 7. Consider this number. That's smart, right? It's made a new number that ends in 7, and it's definitely it's bigger than all the prime numbers we have. And of course, then there's going to be some nonsense at some point. So let's have a look at the nonsense. So here's the nonsense. This is the hard part, right? If n's got a prime factor that doesn't end in 7, then that prime factor must be greater than 5. Okay, but any prime greater than 5 must end in 1, 3, 7, or 9, and cannot end in 7. It just says so. In fact, there's no primes that end in 7. And so it can't end in 7, therefore n doesn't have a prime factor that doesn't end in 7, so n must be prime. So there is no logic at all here, right? The system needs to rule out this possibility, and so it just randomly asserts a completely false fact. Any prime greater than 5 cannot end in 7. You see, it's not thinking, but it is doing what a weak undergraduate would do, right? And given that it's been trained on the internet, this is perhaps not surprising. It's sort of working out. It knows the proof there's infinitely many primes, and it's sort of trying to generalize it and is hoping that everything will work out, right? And that's how we teach, right? We show them some theorems, and then we tweak the theorems a little bit and put those questions on the problem sheet. And the idea is, and the student is supposed to tweak the proof a bit, And that's how it works. So it's writing like a weak undergraduate. So maybe it's unfair asking it such a difficult question. So here's a really difficult question. Let's ask it to prove there's infinitely many even numbers that end in 7. So this is extremely difficult because this is not actually true, it turns out. So you ask it, and it's like, yeah. Yes, they give me proof there's infinitely many even numbers. And it just does exactly the same thing. Say there's only finitely many even numbers that end in 7, and then it makes some new number in some way, and it's just, So that's what you've got, right? That's what you get from ChatGPT, right? They're like a weak undergraduate who's read the entire internet. But they're incapable of having ideas of their own, but they can sort of adapt ideas that other people have had and attempt to make them apply in new situations. So it turns out that they're really, really good at doing school-level exams, right? And this is what when you read the papers aren't saying, actually, these systems are rubbish at mathematics. The papers are written by people with vested interests. They're arguing that these things can get school-level qualifications. And they can. And there's a reason for that, right? It's because school-level mathematics is, firstly, there's a very small curriculum. And secondly, there's an algorithm for marking. Because people, you have to mark like in the UK, you're forced to do mathematics up to the age of 16. So there's necessarily many, many tens of thousands of scripts that need to be marked every year. So there's some kind of marking. Do you mention a certain thing, then you get the point. And these machines are very good at mentioning that thing. And of course, the other thing is there's a huge amount of material related to school-level mathematics on the internet. And so a human, if these exams just failed 60% of people, then they would not be great, right? So the point is, you can pass a school-level mathematics exam without having a true understanding of what's actually happening. And these systems do not have any understanding of what's happening. They're just very good at pattern matching. And so that's why these things are passing school. So you don't be confused. When you see claims that like these things are passing, basic undergraduate level or school level exams, don't be fooled, right? These large language models are not thinking. And in fact, there's reasons why actually making them do even undergraduate level mathematics, it would involve this extremely difficult problem. You would need more appropriate training data. So, but forget about rigor. What about writing plausible documents? This is exactly what they're going to get better and better at doing. And I can completely imagine in my inbox in 10 years' time, there will be people that will be sending me elementary proofs of Fermat's last theorem, which do look very appealing, which have been written by a language model, and they won't stand up to scrutiny. These examples I showed you, they don't stand up to scrutiny, but they look good. And as time goes on, these things will look better and better. So there's large language models. So I'm not worried about being replaced by a large language model, but what I am worried about is some of the other things. So behind a large language model is a neural network. And what's a neural network in general? Well, I guess, at least if you're using it for something like deep learning, a neural network is a computer program which is able to create a formula given a bunch of data. You give it some data, the data is like the input and the output, and you say, I don't know what the function is, but I've that bunch of inputs and the outputs, and you give it the neural network, and the neural network says, okay, here's a function. Maybe this will work. And you try that function on the inputs you taught it, and it does very well. So this is the situation. You've got a function. You want the system to learn the function, and you've got the inputs and the outputs, and so you're going to train that. You don't give all your secrets away. You give, say, some percentage, say 90% of the inputs. You give it to the network, and you say, okay, these are the inputs, that's the output. And then the network says, okay, I've got some function, here it is. And then you look at what the function is, and it's just some completely incomprehensible, gigantic formula that you can't understand at all. So it's a sort of piecewise linear, but highly non-linear thing. So you can't hope to understand what the output is, but then you've still got this 10% of stuff that you kept behind. So now you test the function on the remaining 10%, and now one of two things can happen, right? So, it might turn out that, for the inputs where you didn't tell it the output already, it might turn out to be just guessing, no better. It gets the right answer no more than chance would. Or sometimes it turns out that the network can guess the right answer incredibly accurately. So this is one aspect of this whole branch of computer science. It's very much an experimental science. You're sort of experimenting with different questions. You try these different questions, and a lot depends on exactly how you ask the question as well. I'll give you an example of that in a minute. But this is really, there's not sort of an algorithm for using these things in your work. You should just give it a go. So here's an example. We talked about multiplication already. These things can learn addition quite well. So let's make 10,000 examples of 10-digit numbers and their sum, and that could be our training data. We could show that to the network, and then we could start asking it the sum of different 10-digit numbers, and it will typically do quite well. But when you try with multiplication, this thing we've seen already, we could give it lots of examples of 10-digit numbers and tell it the product, and then we'll say, yeah, okay, I'll guess. Okay, now here's my guess as to what this function is, and then you try it on other examples, and it's just hopeless. And the reason it's hopeless is because this is a bad question. This is a bad question for two reasons. This is a bad question because if you want to multiply two 10-digit numbers together, then you should not be using a neural network, right? You should be using a standard algorithm for multiplying numbers together. So that's one reason that this is a ridiculous idea. But the second reason that this is a bad idea is that neural networks work best. Neural networks work best if the question is somehow stable in the following sense. If you tweak the input a little bit, it has to be continuous. You tweak the input a little bit, and the output only gets tweaked a little bit as well. So addition is continuous in this sense. So there's those two 10-digit numbers we were talking about earlier, and you add them up, and there's the answer. And then you tweak one of them. We just change one of the digits in one of them from a 2 to a 5, and then one of the digits changes in the output. But you do the same thing with multiplication. Of course, multiplication is continuous as a function from r squared to r, but when you consider it as a function on discrete sets of digits, so that's the correct answer. That is actually what that product is. Then you change one number here, and a whole bunch of numbers change in the output. And these are exactly the numbers which the system is getting wrong, right? Coincidentally. So multiplication is sort of not stable in that way. And so you have to, it's not just a case of asking a question, you have to ask the right question. So one thing, if you believe these computer scientists, then we're all going to be out of a job by 2030. But before the machines get really good, it will surely get to the point where they can start helping us, right? Unless there's some weird discontinuity, it will get to the point where they can become sort of collaborators. And so maybe a better question is when will this happen? When will they start being collaborators? And the answer to this question, rather surprisingly, is that it's happening already. So in the last 20-odd minutes, 15 minutes, golly. In the last 15 minutes, I'm going to give you examples of how these techniques that I've just been rubbishing for the first half an hour can actually be used if you're smart. This is the point. You have to ask the right questions. You have to use them in the right way. And so here's one way you could use them. If you work in an area where it's possible to make tables, mathematical tables, then you can ask neural networks to analyze those tables. And if the pattern you're looking for is unstable, then the neural network is unlikely to find it. But if the pattern is stable, then the network might find it. And so now the question is the question you're interested, is the question you're interested in, is it stable in this sense? Okay, so here's something I learned from Yang Hui He, as a professor of computer science in Oxford, and he's very interested in applying these techniques to sort of algebra, to geometry and number theory. And his work, he's thought about elliptic curves over the last few years. And let me say something about elliptic curves. So an elliptic curve, we've seen them before, it's a two-variable cubic equation. Elliptic curves over Q. Elliptic curves are two-variable cubic equation. And the solutions to this equation with x and y rational turn out to form a group, which is finitely generated, and so you can get some kind of numerical invariance. You know, this group is the product of a finite group and then finitely many copies of the integers. And the number of copies of the integers that you need is called the rank of the elliptic curve. So here's the question: can we machine learn ranks of elliptic curves? And the answer to that question is it depends what you mean. So the rank of an elliptic curve is this invariant of this cubic equation. So it tells you, the rank is 0 if and only if the number of solutions to the equation is finite. So it's a sort of measuring, some measure of the infinitude of the number of solutions to this equation. And there are loads of tables of these things. These have been computed for probably millions of examples of elliptic curves. So here's a screenshot of the lmfdb.org website, which has just got lists and lists. And, I asked it to tell me all the elliptic curves of conductor between 100,000 and 500,000. And it says, oh yeah, I've got 2.4 million of those. Here's the first few. And so here's I don't know if you can see them, but here's a bunch of cubic equations in two variables. And then here is these numerical, here's the rank there. 0, 1, or 2 for each of these examples. So can we use neural networks to predict ranks? And it turns out that no, not naively, because the rank is not a stable function of the input, right? We've got, there's our cubic equation, y squared is xq plus ax plus b, and then we're going to change a or b by 1, and we're going to hope that the rank stays the same. Like the idea, if let's say the rank stays the same if you just change a or b by 1, but if you change them by like 10 or 100, then it jumps, right? That's not how it works at all. So you can sort of see if if you change A and B a little bit, the real solutions will only change a little bit, right? The graph will only be slightly deformed. So maybe sort of topological questions might be stable. But if you know all the rational solutions to this equation, then you know nothing about the rational solutions to this equation. Because that's just the way of it. You can multiply both sides by 4 over 3, and then we could change y by the square root of 4 over 3. But that problem is that's not a rational number. So this is a highly unstable function. The rank is a highly unstable function of A and B. But it turns out, this is what I learned from Yang's work, it turns out that actually you can get neural networks to predict the ranks of elliptic curves. And the trick is you don't tell it A and B. You tell it something else instead. You tell it what Birch and Swindon and Dyer were working out. You tell it the number of solutions to the equation mod p for lots and lots of small primes p. And you feed that data in, and then it turns out that the system can start accurately guessing what the rank is. And so in some sense, you're not giving it the elliptic curve. If you know this area, if you're not giving it the elliptic curve, you're giving it the modular form. And so somehow the rank is a stable function of the modular form, but not a stable function of the elliptic curve. This is a slightly subtle thing. And what's happening, of course, if you just fiddle with a few L factors, then you're not changing the order of the 0 as s equals 1. So that's just an example that sort of indicates that the problem is more subtle than you think. So it's not hard to make a neural network that can predict ranks of elliptic curves. And unfortunately, that's a really rubbish theorem, right? This is the big problem. This neural network is great, okay, but what can we do with it? Because we've already got a computer program that computes ranks of elliptic curves. Because I showed you a big table that was, in fact, the algorithms we have, they compute it with 100%. This neural network is predicting ranks with 95% accuracy, but we've got programs that compute it with 100% accuracy quickly, and so we've got a strictly worse thing with the neural. So this is neural networks being used to answer the wrong question. You see. So this is the art now. We've got this tool. Can we use this tool? And what we need to find, you can't just randomly apply it to some question you've thought of. right? You know, so in some sense, one conclusion we have is that rank of elliptic curve is a stable function of the number of solutions mod p as p varies. But we already knew that because that was the Burton, Swindles, and Dyer conjecture. I mean, we don't have a proof, but we already believed it, and now, you know, we just believe it even more. So in the last 10 minutes, I'll talk about examples where these ideas did turn out to be useful. So I thought 10 minutes of harder mathematics was okay. So I'll start with knot theory. There's 4 pictures of the same knot. There's tables of knots as well, like there's tables of elliptic curve. This is knot 7-2, apparently. And mathematicians, as I've mentioned several times, they like to attach numerical invariance to mathematical objects. And it turns out there's many numerical invariants that you can attach to a knot. And some of those invariants are real, continuous invariants. So you take the knot complement is a typically hyperbolic 3-manifold, and it has some kind of volume. That would be an example of a real invariant of this knot. But other invariants are integers. So, for example, the knot would bind a Seifert surface, and you could look at the first cohomology of that Seifert surface, and it has some pairing on it, and you can look at the signature of that pairing. So that's an integer invariant associated to that knot, using cohomology theory. And mathematicians have made gigantic tables of these invariants. And so there, again, it's just another screenshot of a random website. There's our favorite knot. There's 7-2 somewhere. There it is there. There we go. It's got, if you can read it, it's got signature -2 and volume 3.331744. So these are lots of invariants of knots that you can calculate on a computer. And in 2021, sort of a team consisting of 2 low-dimensional topologists and 2 computer scientists, they started investigating these tables, and what they noticed was that they took one of the discrete invariants, the signature of a knot, and they took all of the continuous invariants, all of the real invariants, and they used those as their inputs to train. So now you've got, given a knot, we work out these 15 real numbers attached to this knot. Those are the input, and then the output is the signature, this integer thing. And they trained their neural network, and is that even stable? You see, mathematically, that question is a bit weird, right? Because I've got a knot, and then I get 15 real numbers, and then let's say I change one of the real numbers a bit. Well, now there isn't a knot anymore, right? There's no knot that has those things as invariants. So it's sort of difficult to work out if this question is stable or not. But we can try it anyway, and it turns out that the system was able to reliably, again, like 95% accuracy, was able to reliably predict the signature from the 15 real invariants. And this sounds like, now you kind of feel like we might be onto something here, because anything that's sort of relating, discrete things to continuous things sort of sounds like it might be a profound result. And nothing like this was known before. So now what is the invariant? How is the neural network doing it? How is the neural network accurately predicting the signature? The answer is we've got no idea. Right? Because what you actually look at what the neural network does, and it's like, well, you take these 15 invariants, and then you look at these 100 linear combinations of them, and then all the negative ones, you change them to 0, and then you look at 1,000 linear combinations of these things, and then you change all the negative ones to 0, and then you look at one linear combination of what you have, and then you round to the nearest integer, and then that's it. And you're just like, oh. It's not anything that you can somehow understand. But on the other hand, using something called a saliency analysis, the computer scientists were able to tell you, they were able to say which of the inputs were the most important. And so we could go down from 15 invariants to more like 5 invariants. So the computer scientists say, yeah, you wiggle this input a little bit and the signature starts changing, whereas you wiggle this input loads and the signature stays the same. So the mathematicians now have some kind of clue as to what the theorem should be relating, like 3 or 4 real invariants to one integer invariant. And then they took over, right? Then the low-dimensional topologists take over, They came up with a conjecture, and then they proved it. And so we've ended up with a theorem. So this is sort of funny, right? So this is computers, and this was not computers doing the boring work. This was the computer had the idea in some sense, or it pointed out that something was possible. And then, so here it's not the same as Legendre. Right? Here the computer was a collaborator somehow, in a sense that it really wasn't before. It was helping the humans, go in the right direction. So twice the signature of the knot minus the slope of the knot is at most a constant times the volume of the knot times 1 over the cube of the injectivity radius. So there's a theorem that computers played a non-trivial part in the discovery. And more, this has happened, so that was 2021, but it's happening again and again. So around the same time, the same computer scientists worked with Geordie Williamson, University of Sydney. He's interested in Kazhdan-Lustig polynomials, and just the same thing happened. The question was, given some complicated combinatorial graph, this Brouhart interval graph of a pair of elements of a symmetric group, you're supposed to be able to see the Kazhdan-Lustig polynomial somehow, and the network pointed out various things which are happening in the graph that were not known by humans to be important. But the computers, got very excited about them, and then Williamson sort of stepped back and tried to work out what was going on, and came up with a new theorem. And I think, rather than tell you the mathematics, I want to give you this quote by Williamson, trying to explain what's going on. So for me, he says, these findings remind us that intelligence is not a single variable, like an IQ. I think this is a very insightful comment. That's why I reproduce it. Intelligence is best thought of as a multi-dimensional space with multiple axes. Academic intelligence, emotional intelligence, social intelligence. My hope is that AI can provide another axis of intelligence for us to work with, and that this axis will deepen our understanding of the mathematical world. And I think that, so you see, that's what the earlier part of my talk, I'm saying, oh, look, here's ChatGPT failing to do things that look easy. But what's really happening is we're not asking it the right question. And when you start asking neural networks the right question, this is what you get. So let me give you one more example. This is something I learned about. I just like this because I learned about it on Friday at a conference, and it was a talk by the person in the office next to me, who's an algebraic geometer, Tom Coates. He's interested in the classification of algebraic varieties. So we have like sort of negatively curved varieties, which are very hard, and then there's Calabi-Yaos have zero curvature, and then the positively curved varieties, the quotes easy ones, the Fano varieties. And they're computing, he spent a lot of the last 10 years of his life computing a database of these Fano varieties. So he had 10 million 8-dimensional varieties in this database, and their quotients of c to the 10 minus some hypersurfaces by c star squared acting on the coordinate variable. So lambda acts by lambda to the a. Well, lambda comma mu acts by lambda to the a, mu to the b. So two integers a and b on each of the 10 coordinates. So at the end of the day, you have 20 integers, and that gives you some quotient of a complex 10 space minus some hypersurfaces. And the question is this Fano? So they have 10 million of these things, and some of them will be Fano varieties and some of them won't be, but the algorithms they had for working out if these things were Fano were very slow. So obviously, it didn't take 30 years to do it because you parallelized the process. But they had this huge database that had taken a lot of computer time to compute. And they just thought, let's try the same. So none of the people involved in this work were computer scientists. This was Coates and Al Kasperzik and Sarah Veneziale, all mathematicians. But they just thought they'd have a go, because these things are not difficult to learn. So they download some neural network software, and they ask it this question. I've got 10 million lists of 20 integers, and for each of the 10 million things on that list, I've got a yes/no answer. And so they asked the neural network the same question, and they trained it on half of the data, 5 million examples, and then they ask it about the other 5. So these functions run very quickly, right? They're incomprehensible, but they run very quickly. So you train on 5 million examples, and then you ask it about the other 5 million, and it got 95%. So clearly there's some pattern. You've got these 20 integers and a yes/no answer. This is telling us that there's a pattern that humans haven't spotted yet. And it's not telling you what the pattern is, but inspired by the fact that a neural network could do it, they then went and sat down and they found something. Right? They just searched for a simple algorithm which always gave the right answer, and they found one. So that's sort of, it's sort of funny, right? So this is mathematics happening, somehow inspired by computers. So the new algorithm they have is slower than the neural network, which is super fast but only 95% accurate, but it's much faster than the original algorithm they had. So if they'd done this 10 years ago, they would have saved 28 CPU years, which probably cost them a lot of money. But now in the future they can save money. So I should probably stop. Oh, okay, it's my time to stop. But let me finish by let me show you some pictures. Let me show you, Adam. Let me just. I don't want to overrun. So let me just show you. Here's a question in graph theory, and the question is. This guy, Adam Wagner, wanted to experiment about whether this. He didn't use deep learning. He used reinforcement learning. He's got a system where you know what the function is already. There's some function here. These are invariants of a graph, and the question is whether this inequality is always true. And now the idea is you get the neural network to start guessing the graph. So here, this is what I wanted to show you. So there's a random graph on like 19 vertices, and then you ask, how many points does this get? And the idea, you want to maximize your reward, because making your reward positive will be the same thing as disproving a conjecture. So we just let the neural network run on these. So it's constantly, it runs, it's got a graph and it tries it and the conjecture is true for that graph, but then the neural network starts to say, well, what if I remove this edge? Does my reward go up or down? What if I add this edge? Does my reward go up or down? And it just slowly over time, it's got the idea that it should be a tree. Maybe a counterexample should be a tree-like structure, or maybe a counterexample should be a graph that has one vertex of a very large degree, or maybe two vertices of a very large degree. So it kind of keeps going on and on like this, and eventually it sort of stabilizes like that, and it turns out that this neural network has found a counterexample to this conjecture in the graph theory literature, which violates this inequality. So there's just another crazy example of a completely new way of using machines to do mathematics. So that's it, at least for today. I've only shown you some techniques available. And in particular, I've talked very much about mathematics where there are sort of tables that you can analyze. So tomorrow, I will show you another technique where you can hope to do all mathematics, not just mathematics which somehow involves tables. But one thing is for sure, that these tools are capable of adding, what Williamson describes as a new dimension to the way mathematicians work. And I'll finish with a quote by Terry Tao, which I think is very audacious, but he's a Fields medalist, so he expects maybe 2026 level AI, when used properly, will become a trustworthy co-author. So he's not saying they're going to overtake us, but they're going to become more and more useful in more and more areas of mathematics. So that's it. Thank you very much.